Good evening, my dear viewers. We are going to solve mathematics questions on the ACT, the enhanced ACT mathematics test. So the first question is on radical equations. What is the solution of the equation? And they gave us the equation. So uh, square root of x square root of x minus 9 is equal to 8. And the first thing we just add 9 to both sides. So we have that square root of x will be 8 plus 9. So square root of x is 17. Then you square both sides. Okay, you square both sides so that you can get rid of the radical, the square root radical. So we now have that, of course, the square of a square root of a term is the term. The square of the square root of a term is the term. Just like the cube of the cube root of a term is the term. Similarly, the square root of the square of a term is the term. So that's the way it works. So the square of the square root of x is just x. And then 17 squared we have is 289. So that's it. You know, if you have time, it's good to check. If you just put square root of 289, it gives us 17. 17 minus 9 is 8. So this is question 1. Now we can go to question 2. And if you have any question, please ask in the comments. If you have any question. Question 2 is on exponents. Find the we have a parenthesis 1/64, then raised to exponent negative half. That is question 2. One over 64 raised to negative 1/2. So the first thing, you know, there are several things we can do to this question. We can first of all, the exponent is negative. We can make it positive exponent. Law 6 on exponents. Okay, if you remember law 6 on exponents, if we have 5 exponent negative 1, it means 1 over 5 exponent 1. So the base is in this case is 5. The exponent is negative 1. A base with a negative exponent is the reciprocal of the same base. It has to be the same base, but with the corresponding positive exponent. Okay, if I have maybe p exponent negative 2, this will be 1 over p squared. The base with a negative exponent is the reciprocal of the same base with the corresponding positive exponent. The exponent could be integers, it could be fractions. Okay, so if we have maybe k exponent negative 3/4, this will be 1 over k exponent 3 over 4. So that is a loss 6 on exponents. So this gives us 1 over 64 exponent half. That is loss 6 on exponents. Then the next thing is we want to use loss 7. Loss 7 on exponents deals this with the radicals. Yes, fractional exponents gives us radicals. Fractional exponents, they give us radicals. For example, if I have square root of x, this means x to the half. If I have p exponent 3 over 5, this means fifth root of p cube. Fifth root of p cube. You can also write it this way. You can also write it this way. Fifth root of p all cube. Okay, so this is a loss 7 on exponents. So when we have the denominator here, 1 over 64 exponent half, this gives us square root of 1 over 64. Okay, it gives us square root of 1 over 64. So 1 over 64 exponent negative half is the square root of 1 over 64, which is 1 over 8. 1 over 8. These are positive square roots. Okay, so this here, from here, we now have 1 over 1 over 8. So this is 1 divided by 1 over 8. 1 divided by 1 over 8, which gives us 1 times 8 over 1. And that gives us 8 as the answer. That gives us 8 as the answer. Okay. Go to question 3. Question 3. Question 3 is on fractions, decimals, and percents. It says, from which of the following fractions does the decimal expansion require one repeating non-zero digit? For which of the following fractions does the decimal expansion require one repeating non-zero digit? So we have repeating decimals and terminating decimals. Okay. The terminating decimals are the exact decimals. When we have if we're converting fractions to decimals, how can we tell whether it's going to give us a terminating decimal or a repeating decimal? So we look at the denominator of that fraction. If the denominator has the prime factors of 2 or 5, then that fraction will give us a terminating decimal. If the denominator of that fraction does not have prime factors, so we'll just take the prime factorization of the denominator. If we take it and it doesn't have prime factors of 2 or 5, then it will give us a repeating decimal. So if we look at the options, 1 over 4. The denominator is 4. So 4 uh, 4 is 2 and 2. These are the prime factors. So this will the fraction 1 over 4 is going to give us an exact decimal. Okay, it will give us an exact decimal. That's the terminating decimal because uh the the prime factorization of the denominator gives us 2. Okay, if it gives us 2 or 5, then the fraction will give it will be an exact decimal. The next one is 3 over 5. So 5 already is 5. So this will give us terminating decimal. The next one is 8. Yeah, 5 already is the prime factor, so that's okay. It's gonna give us a terminating decimal or an exact decimal. The next one is 5 over 8. So we look at 8. This is 8 is 2 and 4. And then we do 4. 4 is 2 and 2. So this still gives us 2's. So this will give us that fraction 5 over 8 will be an exact decimal. Okay, it's going to be a terminating decimal. Then the last option is 3. 3 is also a prime factor. So this will give us a repeating decimal because it is not 2 or 5. So it's going to give us a repeating decimal. Okay. Then we go to question 4. Question 4 is on probability. And specifically, probability, the concept there is law of large numbers. So when a fair coin is flipped a large number of times, the number of heads should be approximately equal to the number of tails. So this is just an explanation of the law of large numbers. If you do an independent event repeatedly for a large number of times, then the experimental probability should be approximately equal to the theoretical probability. That's what this law of large numbers tells us. So in this case, if we, this is when you random independent events where you just flip coins, could land on a head or could land on a tail. Okay, that is if it doesn't land on the uh, that's if it lands on the sides. Okay, either the head or the tail. It doesn't land on the corner, the rounded corners. Okay. So when you do it a large number of times, then you should expect, if you do it like 1,000 times, then you should expect to have approximately 500 heads and 500 tails. If you do it maybe 4 or 5 times, it could keep landing on head because those are not large. Yeah. Now it says there, assume that the fairness of a particular coin is being investigated. Some people when they use loaded coin instead of fair coin. So with a fair coin, then you should expect this. But if the coin is loaded, then it's not fair. Okay. The probability of the individual probabilities are not the same if the coin is loaded. So, because the probability that you will get a head when you flip a coin, that's 1 over 2. The probability that you get a tail is 1 over 2. That is if the coin is fair. But if the coin is loaded, then the probability the individual probabilities are not equal. So it says, which of the following results provides the strongest evidence that the coin is not fair? Okay, so the law of large numbers, large number of times. This is the key word that when you do this, you have to do it a large number of times. So in this question, you look at which of these flips is the largest. That's the 6 flips is the largest. You would expect about 3, when you flip a coin 6 times, then you will expect about 3 heads and about 3 tails. But now this is 5 of the 6 flips we ahead. So that can be evidence that it's not fair. Look at 6, because somebody might argue, hey, 6 flips is not allowed. I know. We are working with the options that we are given. So we look at the most that's the most likely option. Okay. So that would be this here, this option here. All right. Question number 5 is on linear inequalities. Who plans to save $200 for a summer skate park pass? So this is her goal. She wants to save this amount of money. She already has $45. This is what she has already. Then plans to save $15 per week. Per week. Per week. So if you're looking at this right away, you see a linear function that this will be the slope, okay, and this will be the y-intercept, what she has already, and then slope per week. That is, if you're looking at this statement right here, okay, it goes towards like, look, observing it right away. See, something like a linear function there. What she has initially, and then what she now has per week. The input being week, and the output she'll be saving being $15 per week. Okay. At this rate of savings, what is the minimum number of weeks after which Anna will have enough money for the skate park pass? So we are looking at linear inequalities. That's why this is linear inequalities. Minimum number of weeks after which she will have enough money for this, which she will have at least, $200. Okay. Uh, so this here, the first thing we do is we can now say, okay, let the minimum number of weeks be W. Okay. Let the minimum number of weeks be W. We define the variables first. We define the variables. So she already has $45, and then she plans to save $15 per week. Per week. So for 1 week, she will save $15. For 2 weeks, she's gonna save what? $30. How did you get 30? That is 15 plus 15, which is 15 times 2. For 3 weeks, she will have 15 times 3, which is $45. For 4 weeks, she will have 15 times 4. Okay. For W weeks, she will have 15 times W. So you see that concept here. Okay, for 1 week is $15, 15 times 1. For 2 weeks is $30, 15 times 2. For 3 weeks, 15 times 3. For k weeks, assuming we used k, that would be 15 times k. So in this case, 15 times W. Now, K needs at least $200. Okay, so we're going to do greater than or equal to $200. If you look at this there, you see 45 is in dollars, 15W is in dollars, 200 is in dollars. You know, that's the way you will set it up. Okay, so we can go ahead and subtract 45 from both sides. Okay, we can, we can subtract 45 from both sides. I know some people like to do it this way. And then we just have 15W greater than or equal to 155. Then you can divide both sides by 15. So I like to, if you're gonna do all work, then you might just want to write it again here. It's up to you. I know some people just go ahead and write it. So our W will be if we do this gives us a repeating decimal. Okay. What do I know is a repeating decimal? Of course, this here 15 cancels 15. Then here, how do I know that this will be a repeating decimal? If you take the prime factorization of 15, 15 gives us 3 and 5. So this 3 is the problem, this 3 here. This is why, it's a repeating decimal. Okay, because no, this really occurs, when you simplify it, it's good to simplify this. Of course, if we simplify that, uh, for you to actually see what I mean, uh, this will be if you divide both sides by 5, okay, this will be 31/3. So it's because of this 3 here. It's because of the 3 here. That is why we now have this repeating decimal. So, when you have a fraction first, is you simplify that fraction first before you actually do the prime factorization. So this is the first thing we would have done here. You simplify that fraction first, and then you now do the prime factorization. So as you can see here, she needs to work. She needs to work for at least 11, 11 weeks. Because why we wouldn't say 10? Why we wouldn't call 10? Because they're asking us minimum. So why we wouldn't say 10 is because 10 weeks, she still has not saved $200. So, but the question says minimum number of weeks. That's the smallest number of weeks. If we say 10, because we still have remainder, it won't work. It won't be up to $200. So the minimum is 11 weeks. All right. We're going to stop here and we will continue the other questions in another video. Thank you for listening. If you have any questions, please ask in the comments. Thank you.